Good afternoon, everyone. Thank you very much for joining us today on our May 2021 technical meeting, as well as our annual general meeting. Thank you very much for our presenters today to actually come in at very short notice and spending their valuable time along with and sharing their very valuable learning over the years. Just a quick few announcements before we go into AGM. Please feel free to put your questions in QA chat box, which is in the middle center of your screen there. And please feel free to ask as many questions as you like to our presenters today. The other one is that can you please keep your mics muted, as well as to save some bandwidth. Can you please leave your your cameras off as well. With that, I would like to say official thanks to presenters and our team today for the AGM general meeting, which is only happening once a year. In May session, so we'll just proceed with that. Just to say first thing first, a very quick thanks to our to our sponsors who have been very kind to sponsor us for their help and support over the years, and they have been very kind to support our technical sessions. These are few of the sponsors that we have in the branch. So the ones that are in the logos there, these are actually the branch sponsors, and the ones that are in the lower section, they are actually our sustaining sponsor for the Institute of Corrosion in general. So we had 4 new members here, company sponsors: Access, that is from USA, NCIMB, Oil and Gas Corrosion, and Imran. The logo is up here. So there were 4 new members for this year, and I think NCIMB has joined us late last year. But thanks to all who has been supporting us over the years, without whom we wouldn't be able to run these sessions. A very quick overview of the finances this year, because we couldn't really spend much money on our face-to-face meeting because of the COVID situation, but our webinars have been up and running for whole year. So our sponsorship is basically going all the way back to the HQ or ICorr headquarters, where it's put into good use for supporting the Institute of Corrosion, as well as the corrosion engineers all over the world. In quite a few areas, all this money is basically left for us to be used in future as well. So we hope that we would be able to come back to the normal face-to-face meeting, hopefully, and then we'll be very happy to see you in person. So we are currently in 7,000, I would say, plus, which is good for next year. So when we are going back to our normal situations, we will be able to use that money. With that, very special thanks to our committee members who are actually volunteers. So after doing the day job, they have been very kind to actually join us and do great work. I was only the face of the committee for only last 1 year. I was chair one time before as well, but I was only the face for 1 year, but actual work was done by all these kind people who have been actually the great strength behind me, of course. And especially special thanks to Human, who has been actually doing all the work for me, or work with me, basically. He has organized all the sessions, and most of the next year's session is done by him. Nigel has been very great in organizing all the paperwork, all the reporting, and all the communication that we send out, and Zara for doing all the meetings and minutes in the meetings, and doing great work in small sections of the committees. Bryn has been very kind to arrange or manage all the finances for us for this year, and it's been great having him with his experience. Of course, he's been pleasure to work with. Dr. Olu, or Olubayo Latingo, who's Dr. Oli to us. He's been great in finding sponsorship. Without him, we wouldn't be finding these three, four company sponsorship in the very, very hard times of COVID situation. Amir has been great in organizing all the great work. He has been organizing all the face-to-face meeting, but this year he's been very busy sending all the links to everybody who's joined us today. He or she must have seen his name there. He's been kindly organizing all the work. Stephen Tate has been with us for as long as I know, for at least last 10 years, and it's very pleasure for us to actually to announce that he has actually become the vice chair of Institute of Corrosion all over UK, and of course he will be becoming chair in 2 years' time. So he's been very kind to handle all the CPDs and all the Q&As and all the university liaisons he's been doing for years, and he's immediate past chair, so I've been learning quite a lot from him anyway. Dr. Yunan Gao, past chair again, he has been with us for a good time, and he is kind of our website whiz and electronic whiz. He's been doing all the good work on LinkedIn and all the communications you see around and invitations going about. Mei Lian Ling Che. Che is our new membership and young ICorr officer, and she has been working in young engineers program and a great asset to our committee. Lester Seaton was there before me in the committee, and he's been great asset. He was chair as well, and he's been great asset. He's been financial, any committee position, you name it, Alistair was on it. It's always been pleasure working with him. And Miss Lian Ling Bei joined us this year as a new committee member, and as soon as she joined in, she quite happily took over the one of the program coordinator, hopefully coming next year. I'll announce that in a minute. But all this committee, great thanks to everyone. If I have missed any of your contribution, please pardon me. I'm pretty sure you guys have been great, and girls have been very great actually. Thank you very much for supporting all of us and the community as well. Much appreciated for your work. As you can see, quite a few happy faces there. That's all of us. If you look across the picture, you will see great many years of corrosion experience going on there. So I'm kind of not really the youngest one, but I'm kind of the younger guys in the whole committee. And I look up to the people standing next to me. It's been a pleasure working with all. It's been a great year from the technical presentation side, from presentation perspective. We had quite a few very, very good presentations, or actually all of them were very good. In September, we had joint GWI meeting, and then MCF joint meeting in October, where we had a very good run-up for 1 week full webinar, and then the industrial visit from Motioneering, and it was quite a good evening, of course. And then we had ION 3 joint meeting, and then before that we had October meeting, which was quite well attended. I'll show you a bit of attendance hopefully soon. And then in January, we had a very, very busy January. We had 1 full week of joint meetings with MCF, which was quickly followed by our joint meeting with Energy Institute, and it was well received, as well as later on we had the February meeting by Rob Hardy, and then in March we had another very good meeting from Dr. George Sergey. And in April, last month was great lineup of webinars we had with MCF, and it was very, very well attended, pretty much all over the world. we had the audience coming from, and then we recorded most of or all of the webinars and then put them online, and it was very well received. In summary, very well attended ICorr webinars. In fact, the COVID situation has been a bit positive for us because we have been trying new techniques and new ways of doing things for us. And recently we have put all of our webinars recorded. Today's webinar is recorded as well. We have been putting all of them on our YouTube channel, which you can see here, the link there. And then we are announcing all of them, all of the webinars, and we have been doing it for quite a few years on LinkedIn, as well as we are sending out emails. And if you haven't received any email from us, please feel free to drop us a line, and then we will put you or add you to our list, and then you will be receiving constant updates from us. And if you don't find us from there, please feel free to join our Google group, where you can actually find good last 10, 11 years worth of resources, free of cost, free for use. Anytime you can actually use them, access them, and if you need any help, please feel free to contact us. In general, we have very good attendance over the year. It's for last 6 years attendance graph, and as you can see, this year has been great achievement that we have been touching almost 100 every other time in this year, because it was webinar, so pretty much everybody from all over the world was able to join, and we have hit good 133 in January, and about 113 in one of our MCF one of our MCF webinar, and 117 in our November session. So it's been great year for us. With that, the most important business of the AGM is to continue the good work we have been doing over the years, and to keep it continual, so that we can actually provide support and help to all our community members in Aberdeen, as well as now internationally as well. So for Aberdeen committee, we have got a kind of a tradition that the vice chair usually take over the chair position, but we still go through the democratic process of being proposed and being seconded. So Human, Dr. Chetan, who's on the screen, thank you very much for coming on video. Human has been very kind to do the vice chair job last year, and he's been great in accepting the chair position. We went through the democratic process. We have got a meeting every month, so we requested to see if anybody is going to propose him, and Dr. Olubayo Latinvo, who's Dr. Oli to us, of course, proposed him, and then Bryn Robert was very kind to second him, of course, and with that we have elected Human Dr. Chetan being our chair for next year, 2021-2022. Would you like to say a few words with that?
Yeah, just a few words. Yeah, thank you very much, Dr. Ijaz, for this introduction, and I will not take a lot of time from today's presentation. Very interesting topics we have here. I just wanted to take the opportunity, first of all, to thank the committee, as you mentioned, Dr. Ijaz, that they have done a great job this year with all of the challenges that we had this year. Everything was changing and evolving, and they were really flexible to address all of the issues and challenges. And thank you for electing me as the chair and considering me as a suitable person for this position. And a special thanks to yourself, Dr. Ijaz, and our immediate past chair and our vice president, actually, Stephen Tate, for all your hard work and all efforts during challenging 2020 session. I have to agree with you that this COVID situation was quite positive for us. with attracting a lot of international audience and very, very successful events, very diverse topics and expertise from around the world. And I would say will be very successful year ahead if we want to continue with the same process. If you can please proceed to the next slide. Just take you through yeah, summary of what's happening next year. I'm actually very, very excited about the program next year. We have received 17 abstracts based on the call for speaker announcement that we did earlier this year. 17 very interesting topics from, again, international speakers, different universities around the world. So it is a very, very difficult task to select 8 or 9 from these for our monthly presentations. We probably will end up having a few more for our lunchtime sessions that we normally have with MCF, and we had 2 of them very, very successful events last year. So we'll try to cover most of these abstracts this year, but we are at the moment the selection process by committee, and we are going to announce very soon the program for the next year. As I said, it will be very, very diverse program. The other exciting program that we have next year is Young Engineer Program. We are, for the first time, we are hosting this in Aberdeen. There has been a couple of Young Engineer programs in the past few years in London branch, but this year Aberdeen committee decided that we are ready to host this in Aberdeen. If you have attended any of these programs or participated in these programs before, or just watched last year's competition, you will agree with me that this is a very, very exciting program and very rewarding event. So very soon we are going to send out announcement for this year participants in Aberdeen. Actually will start, the program will start from January next year, and there will be a final competition between the engineers in November next year. The other events that are happening this year, which is a part of next year's session, is the first one is annual Corrosion Forum, which we used to call them CAD or Corrosion Awareness Day. This is going to happen in August. We are at the moment checking with the sponsor, host, and speakers for the venue, and to make sure that we are ready to have a face-to-face meeting in August. That's the plan. If there will be restrictions, we will probably reschedule this, but the plan at the moment is to have it in August. The last one is ICorr training course, which is also happening this year in Aberdeen. This is fundamentals of corrosion for engineers. There are a few of the course presenters that they are going to do this year, and we are actually again checking for the best time and venue for this course. So that's all happening this year and next year. The plan is to have virtual meetings probably in 2020, and we'll start opening up the face-to-face meeting from 2022 next year, and then probably if we can arrange that, we will still broadcast the events even if they are happening in Aberdeen. So worldwide, everyone could have these presentations live and ask their questions. But of course, everything will be recorded as we have done that this year. And thank you very much again. Back to Dr. Ejaz to introduce today's presenters.
Cheers. Thank you very much, Human, for your kind words. And yes, I'm very much looking forward towards the Young Engineers Program. And of course, it's going to be quite huge success there. With that, our AGM meeting is finished, and we would be very happy to answer any of the questions you have towards the end, and please feel free to put those ones in your in your chat box, and we would be very happy to answer those if you have any questions on the AGM or on any of the agenda items that we have discussed in our AGM. With that, I would like to introduce our speakers for today. Who has been very kind to present their kind work, very interesting work actually today. Second of our speaker today is Chetan Laddha, who is Technology Strategy Advisor in Sinclair Energy Partners Limited. Chetan is subject matter expert on sensors and analytics of integrity management and flow assurance applications. Chetan has a diverse background in the oil and gas industry with the technology development and commercialization roles in upstream as well as downstream segments. He has been involved in development of corrosion monitoring and prediction technologies from early stage maturation and all the way to the field development. And our first speaker for today is Terpstra. Quite a few people in Aberdeen know him, of course, but I would like to introduce him anyway. He's a principal technical expert in Shell. Sigge has over 40 years of experience with Shell and is currently working at PTE as the principal technical expert for inspection and non-destructive examination technologies. Sigge has vast experience of working at Shell, operating assets, as well as in a global role to develop and advance new inspection and monitoring technologies. He's currently based at the Shell Technology Center in Amsterdam. With that, I would like to request all of you to put your hands together, actually virtual hands together, to welcome our guests presenters today. Sigge, if you like, please feel free to take over the screen.
Yeah, I will do. Thank you very much.
Thank you.
And do you see the main screen at the moment?
I do, yes.
Yeah.
Cheers.
Okay, then we did it right this time. Yeah, thank you very much for the introduction. I would like to add, I spent a lovely 4 years in Aberdeen, end of the 90s, enjoying the stay with the family there very much. And by that, I learned a lot of people in Aberdeen. Yeah, the subject of tonight, the presentation, is about our what we call WiSense project, about localized monitoring. Together with Chetan Laddha, we are working on the Shell side. I'll come back to that. And I need to show you this page full of text. Summarize it in this way. When you listen to the presentation and you would don't let yourselves influenced buying or selling shares of Shell. I think that is the shortest summary I can give. That is necessary in this time of the year. Brief explanation. Let me move something from the screen here. The WiSense project is a collaboration between Shell, Yokogawa Electric Company, Tokyo, and the Charles Stark Draper Laboratory in Boston. And what we like to explain, WiSense is the name of an internal project in Shell. It's not a trademark or the product name. And in this presentation, we use WiSense as the project name, but also as the system that we develop. Having said that, acknowledgements. We worked initially together with the Charles Stark Draper Laboratory in Boston, and several people, amongst which Franz Schlosser, Neil Patel, Kurt Johnson, developing the technique under the steer of Shell. Then halfway the project. That was 2015. And by the way, we started with Draper 2012. So we are almost 10 years on the way with this project. Then halfway around 2000, what is it? I think N16. Yokogawa, Tokyo-based, came in as the fabrication partner, and Hiroki Yoshino and Miya Kazunori, and a large team on their side. We work with on a weekly basis. What I said before, Chetan, myself, active as the Shell project team, Brian de Vuist, up to last year when he retired. And then we have many staff in Shell in operating units and also in other support functions. I can assure you, if you start discussing connecting such a wireless system onto an IT system into a cloud environment, you get connection with many more colleagues suddenly. Well, what I would like to do with this presentation is show you the technicalities of the technique and what it can do, because it's quite a new technique, and I'll talk you through that step by step. But first, why did we start on it? At the time, I'm talking 2011, we saw that in the commercial market, we had no system that could combine a number of capabilities for monitoring. And monitoring, what you can see from the pictures, we talk about typically carbon steel. That is also what this technique can work on, not stainless, but carbon steel. And then wall loss. Cracking is feasible, but we have not developed it on our side for cracking. There is another technology development covering that. So carbon steel, wall loss damage, localized wall loss. And to obtain a system that provides area coverage, that operates over coating with a distance, a small distance, not in contact directly with the pipe or the coating. Wireless operation with long time power by battery or any other low power device, long lifetime, and it's affordable at the end. So that were basically the aims. And looking at the spectrum of techniques that you could consider, there are a few mentioned here: eddy current, ultrasonics, magnetic flux leakage, and they all have capabilities to be sensitive, accurate, but also drawbacks that they might need a lot of power. All these three techniques are active techniques in the sense that the sensor, the eddy current sensor, and let me activate the laser pointer. The eddy current sensor generates an eddy current in the surface. Ultrasonics generates an ultrasonic wave, and with the traditional MFL technique, the material is actively magnetized by a magnet. And you can imagine that takes power, and that is not a good start if you want to make a system wireless. So we were looking at something that that could operate without using too much power, and still have capabilities to find local defects. So what did that lead to? Towards passive magnetometry. Not too far away from magnetic flux leakage. And I guess you all working in our industry, if you look at the inspection of pipelines, ultrasonic intelligent picks and magnetic flux intelligent picks are being used there. And our technique shares a lot of principles, but it is not actively magnetizing the pipe. So magnetometry-based corrosion erosion detection, a permanent system that provides frequent and repeatable measurements. So it is attached to the surface. It doesn't need contact. It eliminates the need for routine access to the facility benefits for hazardous areas on 1 to C. Low maintenance, 5-year battery life, which hopes will be exceeded, and no internal wiring, no external wiring, sorry, strap attached for simple installation. And basically in the sketch here, in a process unit, a refinery or an upstream facility, the wireless sensors are attached at the locations where you want to do monitoring. They transmit wirelessly their signals to collection points that goes then into the office environment where it is received and the data is analyzed and put on the screen. A few words about the principle. What I said before, passive magnetometry, it is also called self-magnetic flux exclusion. And that is possible because carbon steel material obtains a magnetic field during the process of manufacturing. When the steel cools down, a magnetic field develops and that stays permanently in the material. And this magnetic field inside the pipe is used for detection. And in fact, what is sketched out here, if there is a magnetic field through the wall of the pipe and there is an element of metal missing, then that influences the magnetic flux lines that go through the pipe. Magnetic flux lines need to be continuous. They can't stop. So part of them is pressed through the thin layer of the remaining wall of the steel, but not everything is squeezed into it and part is coming out of the steel. And that is a very common principle that magnetic flux leakage is in Intelligent Pig is using. And then you can see you can pick up this field at the outside. This field behaves a bit like the field that you probably know from a magnet, a north and a south pole that is creating a dipole field. And in 3D, you can see that the field lines go from south to north. In fact, we say north to south. There is a bit of a convention that confuses us so now and then. It is a three-dimensional field distribution. And to prepare you for the next slides, we measure that in a plane above the dipole, and that creates a certain pattern of fields that we learn to read. We talk about a permanent sensing system. Why is that important? Well, it is important because if you look at the middle figure, this is the magnetic field around the pipe, and it's a seamless pipe. And you see that it's quite a irregular magnetic field already, let's say, being measurable outside the pipe. And it's not so easy to detect a defect. And in fact, this was a test condition where we could add and remove a defect a bit artificially. But here is the same background pattern with the defect indication. By subtracting these two fields, you get a fairly smooth background. And suddenly the defect contribution is very clearly visible. And this can be done because the sensors are attached permanently to the pipe and in such a way that they are not moving around. And that allows you to subtract the original baseline from a later measurement where a defect could develop. And this is the principle that makes our monitoring tool working. So again, magnetic dipole field patterns are excluded in the area where the defect is growing. And then the sensors that we put over the pipe are picking up the field and the B, the magnetic induction fields in so-called maps. I'll explain that later. Our sensors have a square of 12 by 14 sensors in a 6-inch by 6-inch area roughly. That is the standard patch size that we worked with a lot so far. These magnetic maps show the localized defects in terms of a dipole field. And then there is a detection algorithm that finds the corroded area by searching for such a dipole pattern. And there are complex defects. If there are complex defects, then the pattern that it searches for is a collection of dipole. And then there is a defect grows analysis package. So there's a detection package and a defect growth package, and I'll come back on to that. That is monitoring by tracking changes in the signal size. It's detecting the growth. And just to show you how these dipoles look like, and I'll ask you to concentrate on the top line. We will not go through all the three, but in the top line there are the three magnetic directions that the sensors are picking up. The sensors, what I said before, are the 12 by 14 array of sensors, 240, and each individual sensor measures a magnetic field in one of the three orthogonal directions, Bx, By, Bz. X is along the pipe, Y is in circumferential direction, and Bz is normal to the surface. And these three fields, they generate a fairly characteristic pattern of a dipole. In the Bx direction, you see a pattern that is in the dark blue a low and then a high and a low amplitude. Sometimes it's called a Mexican hat, a sombrero. Then in the By field, there is the cross, a quadrupole. It is, let's say, two signals, low in one diagonal direction and two peaks high in the other diagonal direction. Quite characteristic. And then there is the more cosine type of signal from, let's say, a high to a low in the Bz direction. It needs a bit of training if you see these signals. I would think also corrosion engineers are confronted with inspection data regularly, ultrasonics, eddy current. Sometimes it looks magic, to be honest. If I cannot always read an eddy current signal from a screen. Ultrasonics I'm fairly familiar with, but eddy current is a very different technique that also holds for magnetometry. So it needs some training to read and recognize such signals, but after a while you will get familiar with it and recognize the patterns more easily. This is something, by the way, that when this technique is used more widely, needs more people trained in it, because it is a technique that is used in magnetic flux leakage, but you don't see in magnetic flux leakage the dipole patterns that often at that level. So an overview of the practical activities, and I want to first show you and explain you what is visible in the graph, in the photograph on the right. Here you see the pipe system in one of our refineries where a WiSense patch, as we call it, is put on a bend, a 4-inch bend, and it is monitoring in the bend area. And here, less directly visible, is another one. It's mounted opposite the T connection of this horizontal pipe. This is a system where under deposit corrosion is active, can be active in a rather unpredictable manner. That was the reason to choose this location for monitoring. So what you can recognize in this picture is that the sensor, the dark body, is mounted in a frame, and what is not so well visible is that the frame is attached to the pipe, and you can see it here with a strap and with a strap over there. We have different kind of attachments around the pipe in use nowadays, and it means also that the pads can be taken out of the frame. For instance, if you want to do conformation measurements with ultrasonics, or by taking a radiograph. You can also shoot with a radiograph through the patch, but then you get a bit more clutter in the radiograph. But removing it, keeping the frame in place, replacing the WiSense patch is a procedure that works, and that's a very strong point for the technique. So then to the left, The gaps in real-time corrosion monitoring, how did we try to cover that? Providing area coverage. Compare with, for instance, ultrasonics. If you would like to place an ultrasonic probe for monitoring on a local defect, you need to be pretty sure where the defect is. Otherwise, you might be either next to it or on the edge of it and getting very unreliable signal from the depths of the defect. So you need to be spot on being on top of it. And although ultrasonics is a technique that provides us with the highest measurement accuracy in terms of depth, it is not easy to make ultrasonic arrays working on local defects. So the WiSense patch is providing area coverage, picks up local defects, wall loss. There is no contact with the surface. There is minimal infrastructure impact. The sensor is connected to a wireless device, and unfortunately, not on this photograph. Apologies, we could have taken a slightly different angle. Then you would see a very small box that is generating the wireless signal, carrying the information to a remote point. Long lifetime, what I said before. Initial development between Shell and the Draper laboratory in Boston. Yokogawa taking up development and commercialization. And this year, Yokogawa will come out with the first commercial product. So you will hear, let's say, more about the final commercial versions of this. This is very close to it, but it is a prototype that we used for 3 years since 2017 in one of our refineries. The goal is to achieve a step change in the capability to monitor for local defects, and in that create drivers for cost reduction and asset integrity and life extension. Our current application targets are onshore and offshore topsides, straight pipes, bends, tees, and welds. A few pictures on background testing. I like to present this because testing a permanent monitoring system is not that straightforward. And this is an example of etching a pipe. Why etching? Well, that is because we have a magnetic technique that is sensitive for cold work. So if you start machining defects, you introduce magnetic fields. And particularly in the beginning, we didn't want that disturbance. We later learned you can minimize it to a large extent, but etching a defect gives you the most natural let's say introduction of a defect without disturbing magnetic fields. But then when you want to do the real testing, you want to have the patch left in place, which means you have to introduce the defect on the other side. And if it is a pipe, you need to create access in the pipe with etching agents, letting the etching fluids running off after you drip them onto the defect area. And this creates a fairly tedious process, which is something that comes with permanent sensing techniques. And we see that with other sensing techniques as well. You run one test and then the defects have grown to a certain depth, and then you put the pipe aside and start with a new one to generate a second test. We did this with the Welding Institute as an independent set of trials, and that gave us opportunity not only to measure the defects, but also to create reference data by measuring with laser imaging and replication and ultrasonics, measuring actual sizes in various stages of the growth of the defects. You can imagine that is data that you don't get that easily from a running plant, where you might, if you're lucky, get so now and then an ultrasonic reading. So, illustration of something that relates to the analysis process. What I introduced a few slides ago is that with magnetometry we try to measure dipoles, which are in fact ideal dipoles as point sources. But real defects have a certain extent. And that means that also the field generated is not the pure dipole. And that means that we had to develop a sort of a modeling that the magnetic field is modeled coming from an extended area. And that is then translated into what we call templates. And when a patch is developing a detection of a magnetic field, then the algorithm is starting to try to match a certain defect template with the measured field. And it is going through thousands and thousands of model templates, trying to optimize the match between what it actually sees and what is in the database of templates. And this leads to a very good detection. One other thing I like to say, if you try to identify a dipole, the dipole has a lot of redundant information. It has a pattern in the three directions of the magnetic field, the X, the Y, and the Z. And that pattern can be detected when the amplitude of the signal is in fact still in a noise level. So that means you can start seeing the presence of a dipole when the human visual eye is hardly recognizing anything yet in the noise level. So here a few comparisons. I don't want to bother you too long with these pictures, but what you can see on the left side, I will limit myself to the information on the left side, is that here in this column we have the measured field Bx, By, and Bz, and then hang on, excuse me, the middle column is the matched template. And you can see if you compare the measured field and the template, you see a reasonable correlation also in the size of the dipole field. If you would use a simple point dipole model, you can see that there is a much larger discrepancy. And this illustrates that using that template that represents a defect of a certain length, a certain width, and a certain orientation in the magnetic field is making a good match with what you actually measure on a defect. Now, highly technical, I want to leave this for a while. And introducing the two algorithms that are supporting the interpretation of the magnetic fields that the patch is picking up. What I said before, it is based on first subtracting the baseline. So what you measure on day 1, day 2 is taken as a baseline, and then you subtract it from all the subsequent measurements. And typically we collect with this system 1 measurement a day, midnight, to reduce all sorts of temperature effects that might introduce small variations. So a very stable midnight measurement in a day frequency. And that has proven for corrosion mechanisms to give you a nice measurement sequence that allows you to see a gradual change when the defect is growing. First, the detection algorithm is doing its work. It is comparing in the top row the measured magnetic fields with these templates and trying to optimize the match with the template. And that shows the direction of the dipole. You can see there's a slight angle in the dipole. It's picking that up. Also the size and the magnitude of the field. Then it goes into what we call depth profiler to monitor the growth of the indication. And that is taking the data and identifying what the extent of the defect is. This is done in a profile, a graphical profile represented. Same information as in the heat map on the left. And this is on the display of the screen of the end user. And over time, and I will show you later a series of measurements of real defect. You can see the evolution of a defect growing. On the practical side, if you look at what you could in principle achieve with measuring with magnetometry and mounting patches on locations where you expect local damage, I think you immediately recognize the typical locations where due to flow disturbance, deposits, injection, you can have aggressive local corrosion, and that is where the technology is able to work. It also works on top of a weld, which means that any pitting generated in the root of the weld is also measured. And that's a strong element, a strong aspect of the technique, because if you look at the inspection side, you need much more complicated NDT, non-destructive testing techniques, to measure what is going on in the root of a weld than in the parent metal next to it. So the capability to monitor over the top of a weld is a very strong one. Then the practical side of installation. Here there is a photograph with the patch, and now with the wireless device strapped on the support next to it. Here you see another situation with a device, and the wireless devices are connecting in an ISO 100 network to an access point, which is then routing its data to a gateway. And from the gateway, it is arriving in the, let's say, the cloud environment, which can be an end user cloud or a cloud supported by Yokogawa. And we have at the moment, let's say now we have the patches running, a lot of work to get everything running in an Azure IoT cloud. That's still quite a step to get that, let's say, properly working. Unique position of WiSense for localized degradation. If you look at the mechanisms, then it's only on the right end where ultrasonics is, let's say, the champion technique, uniform corrosion. You probably know of PermaSense probes, the first wireless monitoring devices in our industry that found a very broad market. Perfectly working on uniform corrosion and extensively used in the refinery where there is high temperature sulfidation, creating very uniform corrosion. But as soon as you go away from that mechanism, then a lot of mechanisms can become, although sometimes a mix, but can become extremely local in the attack of the wall. And I don't need to explain you anything about this, but it is the challenge for inspection, but also for monitoring, to get devices that can detect the onset and the growth of such local defects. Well, here is an example of one of the patches from our field trial. And you can see December 2017 was when the patches were installed in the refinery. And this graph goes all the way to October 2020, so end of last year, and showing the, let's say, initial stable condition. And then we saw the statistical, the blue bars, the statistical indicator going up, telling us that there is a change in signals and that there is a clearly detectable signal present. And then with the gross monitoring tool, the depth detector, with the orange line, it showed the growth of the defect, and then becoming stable with a slight variation, but virtually stable. We missed during a turnaround and also a subsequent error in starting up the sensors. We missed a window, but then fortunately, saw it coming back on the same level, and then another excursion started. And this is where the power of the monitoring comes in. If we communicate this to our corrosion engineers and also the technologists, the process engineers together, where they can start working on correlating such start and stop behavior of defects with the process conditions, and how the process conditions then influence the corrosion rate, the aggressiveness of the corrosion mechanism. What the end user is seeing on the screen is, as an example here, a series of images that are taken over different times in this whole trajectory. Nothing in the beginning, gradually a defect coming up, and then you can see becoming more and more intense in color, growing, which is in fact represented by the amplitude of the orange line. And you can see this in a certain location of the patch. Yeah, by that you know where the defect is growing and what roughly the extent of the defect is. So WiSense analysis comes with two capabilities: defect detection, which in fact is a yes/no indication, because there is the red line, the threshold, and if the blue bars are above the threshold, it signals a positive detection. And then it is the second algorithm that tells you what actually is going on with the defect in terms of its size. So conclusion summary: WiSense technology introduced for local defect monitoring capability and is an important inclusion in the NDT toolbox, alongside other inspection and monitoring techniques. The WiSense technique has demonstrated robust performance over 3 years of pilot testing in multiple assets. We have been, you saw the photographs in a downstream environment. We're also monitoring for 1.5 years in an upstream land-based environment. It's highly sensitive for localized degradation, and it allows proactive monitoring and prediction of pipe integrity when used alongside simulation and prediction tools. Highly sensitive in the sense that if we try to confirm defects that are in the early stage of detection with ultrasonics, quite often we are not able to distinguish them reliably. Then we talk about a few tenths of a millimeter depth of defects. And it is applicable on process piping, and it's carbon steel. Please remember that it's not working on stainless steel that doesn't carry magnetic fields to that level as carbon steel. And the environments where it is applicable is onshore, but also subsea pipelines, carbon steel pipelines. So with that, I would like to stop my presentation, and thank you for the attention. And if you have any questions, try to do with Chetan, try to answer them. Thank you.
Ajos, do we take questions first, or can I move on to the second one?
Yeah, I would actually request you to present first, and then probably we will just put forward the questions as a panel, if that's okay with you.
That's absolutely fine.
Yes.
Thank you.
Cheers. Thank you.
So hopefully everybody can see my screen.
Yes.
Quick check. Perfect, brilliant. Good afternoon, everybody. I'll not take, I think I'll aim to finish in the next 10 minutes or so we have time for Q&A. You know, the last point that Sigurd mentioned was about you know, having corrosion monitoring techniques and then being able to use alongside modeling techniques. So we wanted to show you a little bit about an example of a modeling technique that we have been working on. So from a positioning perspective, you know, why did we start this effort? So this is really about trying to understand and model the mechanism behind inhibited corrosion rates. One of the challenge with modeling inhibitor performance is that the inhibitor chemistry is, of course, you know, as we all know, is a black box, you know, for you know, good commercial reasons. And for any system where we do not know what's inside it, it's a very difficult problem to be able to solve. And it's very difficult to model, you know, a compound which you don't know what's in it, except, you know, what's in the MSDS sheets. So state-of-the-art simulations or models like, you know, DFT or others, which otherwise could be used, it is really, they cannot be used for modeling what a corrosion inhibitor will do in a hydrocarbon stream. What the common approach that's used in this industry today is to have models which give us uninhibited corrosion rates, and there's plenty of models which do that. You know, some empirical, some mechanistic. And then the traditional approach is to have CI qualification programs. So corrosion inhibitor qualification, where the inhibitors are tested on a range of operating conditions, and those tests give us inhibitor efficiency. And the traditional approach is if we take the uninhibited corrosion rates from the model, multiply it with the inhibitor efficiency, and there comes the inhibited corrosion rate. So the link between the uninhibited rate and the inhibited rate is as you can see, it's a linear or an empirical function. And what we are trying to get to is to expand the modeling capability so we can go beyond the uninhibited corrosion rates and be able to understand what is the performance of the inhibitor? When is it working at its best? What are some of the turning points on its performance? And actually, can that behavior be used to optimize the dosage rates, or really find out the areas where the inhibitor is best in its performance versus perhaps the worst performance? So that led to this approach of what we call inhibitor optimizer, and really the logic here is, because we don't know the chemistry, what we try to look at is the electrochemistry. So instead of trying to understand from first principle, what's inside the molecule and what this will do, what the approach we have taken here is to understand, is to simulate and understand how will this chemical react on a steel wall, and what are those electrochemical reactions which are occurring under different conditions, and to be able to understand those mechanisms, model them, and that's essentially what the model is born out of. So couple of points on the corrosion inhibitor. The most common term used is CI efficiency, which is how efficiently is the corrosion inhibitor able to bring out the uninhibited corrosion rate. And typically, as I was saying earlier, it tends to be a single number, or it tends to be a few numbers that come out from CI qualification. It's common practice that CI qualification can only be done on a certain number of points. We assume that they are the worst case points from an operations perspective, but there is a lot of judgment in that exercise. And from a mechanism perspective, the CI efficiency, indeed, as we all know, it's variable. It does change with variables like a few we have listed here, the process conditions, or what's in the production and how that's changing over time, or even the electrochemical reactions, which electrochemical reactions are governing. And what we have found is that the CI performance is actually quite complex. It's very non-linear, it's very fractal in nature. So difficult to have a graph where we can linearly extrapolate a CI efficiency for let's say 10 to 20 years life of an asset. So I'll give one example of why this mechanistic approach of being able to model corrosion inhibitors is important, and then after that I have a few examples to show on what the model itself can do. So here is an experimental data set which was done with an RCE, a rotating cylinder electrode, under certain conditions. As you see here, the pH, the partial pressure of CO2. And what was done here is a test over 12 hours at 1,000 RPM, and the corrosion rate was, going down from 3.7 millimeters per year to 0.4 millimeters per year, which gives an approximate corrosion efficiency of about 88%. So that's a very good efficiency. If we repeat that experiment with a higher rate of 4,500 RPM, that's equivalent to about at about 10 millimeters per year. I think we would assume that the corrosion rate should increase, and also with the efficiency being 88%. Our corrosion rate at the end should be about, say, 1%. But what we found from the experimental evidence is that even if we increase the RPM, we were still getting the same corrosion rate at the end, which was 0.4 millimeter per year, which gives an even higher CI efficiency. So that's fantastic. That's very good news. But the question is, what if we go the other way around? What if instead of going from 1,000 to 4,500, if we reduce that down to 300, what happens then? Well, the assumption is that naturally the corrosion rate should reduce. But again, the experimental evidence suggests that not really. The eventual corrosion rate was still the same, even though we varied the velocity by quite a margin of between 300 to 4,500. And if we look at the efficiencies between all these three scenarios, the efficiency of the CI is ranging anywhere between 66% to 95%. Efficiencies which are close to 90 or 90 plus are regarded as very good, but 66 is concerning. So this, this experiment sort of asks, it brings up a couple of questions. What is it that is that is changing the CI efficiency by such a big margin, from 66 to 95? And this was just, we were just varying one process parameter. In reality, there will be a lot more parameters which will change, and what will that do to CI efficiency? So this is this problem isn't anything new. About 2 decades ago, a couple of experts from Shell, Bird Potts, Kapusta, they had described this 2 decades ago that the evaluation of corrosion inhibitor isn't really, it can't be done by looking at the initial and final corrosion rate, and the efficiency is really not a good way to look at it, because efficiency is, number one, not constant, and number two, it cannot be linearly extrapolated. So the question that it arises is this was only one variable which we varied. What if we change other variables? What if we change, let's say, the temperature or pH or any other conditions? What will that do to the corrosion inhibitor performance? And it's essentially these questions which we're trying to answer with the mechanistic inhibitor model, to be able to look at the underlying mechanisms which are occurring in the presence of inhibitors under different conditions, under different concentrations, and then to be able to simulate what will that inhibited corrosion rate be. I'm conscious of time, but I'll walk you through a few more examples. The traditional sort of modeling approach for inhibitors called blockage effect, some of you may be familiar with this, but essentially it assumes that the corrosion inhibitor, it covers majority of the surface. There is some surface which is not covered, and that's what gives the CI efficiency. The test we have done suggests that that's really not true, because otherwise the graph that you see here between the potential and the total current, between the uninhibited rate versus inhibited rate, it should not show such a difference that we saw here, a big reduction in the current. And also, other experimental evidence to show, especially the one on the bottom right, where the limiting current for a number of inhibitors at different concentrations was very much in the same ballpark, which asks this question that, well, if the inhibitors are changing, the concentration is changing, why is it that the limiting current is not changing? And that's essentially because the governing electrochemical mechanism is what drives the corrosion rate. And in certain cases, it's the limiting current, which is the governing mechanism. And in certain cases, it's the charge transfer, which is the governing mechanism. If we can model these two mechanisms, from a mechanistic perspective, and understand which mechanism will be active in what scenario, that's what is able to give us a mechanistic way of simulating how does corrosion rate, the inhibited corrosion rates, vary with operating conditions. There's a lot more material, but it's 7:10, so maybe a brief, one more brief example to show. I talked about the rotating speed as one example. Here's an example where this is just simulated data, where if we have an uninhibited corrosion rate, which is changing as a function of the superficial velocity, and if we have, let's say, an assumed 90% efficiency, that gives a corrosion rate graph which would look somewhat like this. But then what we model from the electrochemical perspective is quite different. That model says that the corrosion rate in this case, in this simulation, wasn't really changing as a function of the velocity. And then when we backtrack, that gives a curve of the model efficiency, that the inhibitor efficiency was indeed changing from by quite a margin. So there's a few more examples in the slides where we have a case study where we change the speed, we change temperature, pH, concentration, and then we are able to see in all those scenarios that the inhibited corrosion rate could at times, and several times, be higher than what we would otherwise assume by just going with a simplistic CI efficiency based approach. So that's everything. I believe a snapshot of what the model looks like. So we're able to simulate CI across different process parameters. A few examples there are the velocity, temperature, pH, partial pressure. And then we are also able to sort of backtrack with what are the governing electrochemical mechanisms, which is giving us this answer, and in how that is varying with the process conditions that are expected over a long period of time.
Okay, thank you very much, Chetan. Yeah,
sure.
Thank you. Two very interesting presentation topics. Thank you very much, both of you. There are a few questions, so I will go through them. Yeah, as you mentioned, don't have that much time. So I will start with the question regarding the first presentation. Many thanks from the talk about the talk, and the question is, I was just wondering about the temperature limitations for this equipment. Can you advise, please?
Yeah, sure. I can say something about that. Good question. The patches are at the moment being used with a very short distance to the pipe, so they pick up the heat from the pipe despite a small gap. The electronics is specified for up to 80 degrees. Okay. So the patches operate very nicely in upstream environments, also in other type of conditions, low temperature. We have looked into bringing the patches to higher temperature. One way is putting highly insulating material in between the pipe and the patch. That brings it up. We have done modeling in the range of 200 degrees. That is an area that needs to be experimentally tested much further, particularly now the new commercial patches are available. There's also potentially longer term improvement that the electronics is redesigned, bringing it up to slightly higher temperature. Then in combination with insulation, a higher temperature range is achievable.
Okay, yeah, great, thank you. Actually, one question myself about inspecting the insulated item. So what is the limitation for the insulation thickness and any cladding on top of the insulation?
Yeah, we have tested it up to a few inches, but went back to operating the patches very close to the surface. That is where you get the strongest signals. And there also we get the highest sensitivity for local defects. The magnetic fields are not disturbed when they go through insulation material, or they have to pass the metal cladding when that is stainless or aluminum. A slight reduction when it has to pass to carbon steel, but there is not a skin effect like with eddy current in place of magnetometry. So it also gets through a small layer of steel. So yes, it works on a distance. We have tested it, but magnetic fields drop off very rapidly as a function of distance. So you quickly lose sensitivity when you go to larger, over an inch, 2 inch, 3 inch distance. But certainly the technique works, and there are other technologies with magnetometry that utilize it on a larger distance of a pipe.
Thank you. There was another question regarding the if it is applicable on the cylindrical surfaces like pipeline or vessel.
Yeah, it's in fact not very dependent on the function of a let's say a steel pressure envelope, be it a vessel, pipeline, material, or a piping. What counts is that the defect is that you're growing at the inside of the pipe, and then what matters for the detection sensitivity is the distance to the defect, the standoff from the defect to the patch. So you can imagine if you would like to monitor on a 100 millimeter thick pressure vessel wall, then suddenly you talk about 104 inches standoff, which is well beyond what we have tested so far. All the work has been around pipework, where with a wall thickness of half an inch in that order of magnitude, 3/4 of an inch, the patches are fairly close to the defect.
Yeah, okay.
I hope that answers.
Yes, of course.
The question.
The other one probably again, because there is no need for contact to the surface, is asking about if the weld need to be ground flat. I don't think that's the case.
Yeah, no, that's a good question. Because it works at a slight standoff, 10 millimeter easily. That means it can easily accommodate the cap of a weld. And you can put the patches over a weld in.
Yeah, great. The other question is that if there is there any interference from magnetic particles, ions, or solids from the weld fluid?
That's an interesting question. I don't think we have seen effects of the fluids or anything carried with the fluids. But yeah, I know from experience with several monitoring techniques, when you go to high sensitivity, you always have to be, let's say, on your guard with layers that might form itself on the inside, and particularly when they have a magnetic property. So far we haven't seen that. What I can say, what we have seen is that if a pipe is part of a large plant, there are magnetic fields in the plant that might change over days, and that creates what we call anomalies in the background field. And as I have explained before, we do baseline subtraction. So when you have a change in the magnetic field, then that would affect the measurement. Fortunately, and this is the value of the field testing. Fortunately, the changes that we see are of a very sudden nature and can easily be removed from the signals. And that has become part of the data processing to clean the background again from these quite sudden jumps.
Okay.
And of course, there is the regular noise levels and that you find when you go down in sensitivity.
Yeah, if I can just add to that, Seeger, indeed, one of the things we have done as part of the field testing is to be able to understand that yes, we will get anomalies in the field, no doubt, but then we are able to compensate. We have learned and tested and tried techniques of different ways in which we can compensate and still sort of maintain the long-term monitoring trajectory.
Thank you very much. I think that the last question about the first presentation is actually from Humphrey Ezifedi, because he's asking about if this presentation is done for Shell corrosion engineers as well or not. Probably he's from Shell.
You're asking whether it has been done internally in Shell. Yeah, and also more extensively. What I can say is we are preparing for the rollout of the patches. We have seen them as prototypes being tested, but very soon now the commercial versions, I should say, become available via Yokogawa's delivery. That will not only be to Shell. Yokogawa will be looking for a global market for these patches. So our hope is that it raises interest with many operators, that they start considering using these sensors.
Okay, great. Thank you very much. So
welcome.
There are a few questions for the second presentation for Chetan. Sure. So the first one is, how does the model differ from other alternates such as NORSOK, ECE, etc.?
Yeah, no, that's a very good question. So there are a number of models which are very widely used to be able to model different types of corrosion, CO2, H2S, and others. The main thing is that those models only give us the uninhibited corrosion rates. And then there is there is almost an entry block in each model to say, please enter your inhibitor efficiency, which comes from the CI qualification. And you put that number in, and then you get the real inhibited corrosion rate. And it's that number that we are saying that instead of having one number that is entered or a few numbers that are entered in the simulation, why don't we mechanistically model how is that behavior changing over time, and with the process conditions. So that's the main difference between the models that you mentioned, the ECE, NORSOC, and the likes of these models. So I would say they are very complementary to what we are trying to develop. They sit next to each other.
Yeah. Okay. Actually, it's relevant to this. I have myself a question. So if someone is preferring to have like uninhibited corrosion rate by ECE, can your model use as add-on to an existing model to adjust the uninhibited corrosion rate to an inhibited corrosion rate?
Yeah, and that's precisely what we're working on as well, to have the capability to put this tool in the cloud, so you can connect this to any other model, which can go as far as the uninhibited rates, and then this can kick in for the inhibited corrosion rates. Yeah.
Okay, then it can be a combination of mechanistic and empirical model both together. Yeah.
Absolutely.
Okay, thank you. And what is the limitation of the model?
Yeah, very good question. Every model has limitations, and this is no different. So this is one last slide that I didn't get to. Current capabilities we have is to be able to model the inhibitors under the operating conditions. What we are not able to do at the moment in terms of our future developments for short term is to be able to expand this to H2S. Currently this is only for inhibitors for CO2 corrosion. And then to be able to model performance of, let's say, the enhancers like thiols, or to be able to model the impact of organic acids. In the longer term, we talked about the electrochemical approach of trying to model essentially the behavior of corrosion inhibitors. And then in the longer term, sort of our plan is to be able to expand that to scale inhibition. But on your question of the limitations is on the right-hand side, that model assumes the best possible outcome in terms of the corrosion inhibitor efficiency in the bulk. That's one assumption at the moment. Second assumption is that this does not cover batch treatment. So it assumes continuous injection of the inhibitor. Thirdly, the temperature. So at the moment, we haven't really tested it to high temperature. At the moment, it's only up to ambient temperature of sub 80 degrees C. So those are the couple of main limitations.
Okay, that's great. Thank you. The next one is what are superficial velocity limitations in the model?
So as far as I'm aware, there is no limitation to the superficial velocity, but I do have my colleague here, Juan, who can confirm that for me.
Yes, so basically the model, hello everyone, my name is Juan Dominguez. Basically the model is assuming that in this case, we have a correlation between the rotating cylinder electrode and the mass transfer mechanisms associated with a pipeline. So in this case, we use the Eisenberg correlation for doing this. So basically we are just matching the mass transfer coefficient by using the Sherwood number. So basically the limitation for this, I'd say some realistic limitations. For example, if you have a pipe that is running at 3 or 4 meters per second, the model can capture that. However, how realistic sounds that? Because it'll be extremely turbulent. And then those conditions are kind of unrealistic. So basically from the superficial velocity perspective, I think the basic limitation is just to match the mass transfer coefficient associated with this rotational velocity speed with the real ones. So that'll be kind of the limitation and how you trust on these correlations. Of course, if we can do it, let's say, in a realistic manner, then we would cut that limitation by measuring the mass transfer coefficient, but it'll be a kind of difficult experiment. So that's why we need to rely on these correlations. Hope that answered that question.
Yeah, thank you. And maybe a continuation of the same question is about qualification of inhibitor for welds. So it's quite tricky. You have like different efficiency for welded and non-welded items. So how do you address that? Is it one of the parameters that you have considering?
Could you repeat that again, please, Human?
The presence of weld is always tricky when you are qualifying inhibitors. So how do you consider the weld presence? It's one of these geometry stuff.
Yeah, that's a very tricky question. It's a very good question. For example, the nature of one corrosion inhibitor usually relies on absorption, this type of corrosion inhibitors. When we have a welding, we may have a different metal surface that will not allow the absorption of this corrosion inhibitor. So basically what we would need to do is to use the same approach, but using the experimental results from the welding. So basically this model is not a unique and universal model because each inhibitor is different. So instead of saying that this model will account for, I'd say that we need to do some experiments to get the information required to get this model to work. So if we have such conditions, then those conditions needs to be tested. I guess there's no other workaround.
Okay. Yeah, that's definitely case by case. Yeah.
Exactly, case by case scenario.
And the last question, is this model independent of inhibitor chemistry like anodic or cathodic inhibitors, or there are critical assumptions that one should be aware of?
Yeah, so basically the critical assumption is that this is an organic type of corrosion inhibitor. And currently, the experimental observation that we have seen thus far with this type of organic corrosion inhibitors that make a film of the surface is that get the retardation of both anodic and cathodic reactions equally. However, this can be masked because we have a limiting current. And that limiting current is usually not affected by the presence of an organic corrosion inhibitor. And that's why you may think that you have an anodic corrosion inhibitor.
Okay.
So this assumption that the limiting current is not affected by the presence of an organic corrosion inhibitor needs to be tested. So basically, that's kind of the proof that the model works on that particular corrosion inhibitor. So that's why the model needs to be fed with experimental data in order to work. So of course that we may find some corrosion inhibitor that are not candidates for this type of modeling, if it is just purely anodic or purely cathodic. But currently thus far, all the organic corrosion inhibitor we have tested thus far met that kind of behavior.
Okay, yeah. Okay, great. Actually, there is one question I missed from the first presentation. Is asking what is the detection and quantification threshold? Will it be able to detect, for instance, pinhole corrosion?
Yeah, I had to get off mute. Apologies. Yeah, what I did not explain during the presentation is, as with magnetic flux techniques, basically the sensitivity is based on the volume of the defect. That's a rough approximation. But we have seen defects 20 millimeter wide. What I said during the presentation, if they start becoming detectable, very difficult still for ultrasonics if you scan them with a phased array normal beam probe to positively detect it. So at that level, very sensitive. But you can imagine if the defect is becoming narrower and narrower, then there is less volume with a certain depth. This is what we call the aspect ratio of a defect and length over width. And yeah, if you have, let's say, normal CO2 corrosion processes in carbon steel, my experience is, having looked at a lot of local, what we sometimes call pitting defects, they quickly have an aspect ratio of 3 or 5, 3 times, 5 times wider than depth. And sometimes they look extremely local, but then if you take a ruler, measure it, and you discover that it is still in that range. But of course, there are other mechanisms that really can go like a wormhole into the metal. And that is where this technique will see its limits, the volume is then so small that it might miss it. Fortunately, that is the more rare type of defect. But that is a warning. If people would expect microbiological corrosion that would create pinholes, then this is not a technique that you should count on as first. I wouldn't know any other technique, by the way, that has that high sensitivity. It's back to NDT scanning inspection.
Exactly. Yeah. Thank you. Thank you very much.
Welcome.
Thank you, both of you, and thank you, Johan, as well, for answering the questions very detailed.
No problem. My pleasure.
Thanks everyone for attending from my side, and I'm going to hand it over to Dr. Ejaz for some final notes.
Yes, thank you very much, Roman. It was a pleasure hearing you all, especially the interesting presentation there. And with that, I will thank our presenters, Sinclair and Chetan, for their kind presentation, and it's been quite interesting there, and it was quite evident from the questions coming up, which was quite nice to see that everybody involved into it, which was quite good. With that, I would like to thank everyone for attending this presentation today. And with that, this is actually end of our session for this year. And we're going to have a break for 2 months, June and July. And then we would be hopefully be coming back with our one of the industrial visits or annual corrosion forum day, hopefully in August, which is being finalized, and hopefully you will hear from us. With that, thank you very much, everyone. And it's gonna be next session with Human being chair, and quite feeling relieved. But no, I would say thank you very much, everyone, for joining us today. Much appreciated, and have a very good evening, and stay safe, and stay well.
Thank you.
Thank you.
Thank you very much.
Thanks, everyone. Thank you. Good day. Bye.
Cheers. Thank you. Bye.
Bye.